Hello everyone, welcome back. Hope everyone is staying safe and healthy and is able to continue learning in this weird new virtual environment. I welcome you back to lab. As you can see, I'm still here coming to work, trying to help you learn as much as I can. And today we're learning about equilibrium. And specifically, the lab will be devoted to looking at some experimental examples of Le Chatelier's principle. So let's talk about what Le Chatelier's principle is. You probably know this from lecture and discussions with Dr. Blas, that Le Chatelier's principle states that if a system is at equilibrium and a stress is applied to such system will typically react by shifting equilibrium in such a direction as to relieve or minimize the stress. And so I'm going to talk a little bit about some theoretical examples, and then I'm going to show you the actual experiment, and we're going to discuss what's happening in each case. So first of all, what is chemical equilibrium? Very often people don't really understand what it is. So I'd like to first explain that equilibrium in chemistry is referred to a situation where reactants and products undergo two reactions at the same time. Forward reaction where reactants are converted into products, and reverse reaction where products are converted back into original reactants. Not only that, but to say that chemical equilibrium has been achieved, we must have a situation where rate of forward reaction is exactly equal to rate of reverse reaction. So if you were sitting there looking at say a test tube or a flask or a beaker where chemical equilibrium would be occurring, you would not notice any change in the appearance of your reaction mixture, because to your naked eye it would appear as though nothing at all is happening. And so how can we put a stress on the system? Well, the first example we're going to consider is changing concentration of a reactant. So say we have this hypothetical reaction between A and B, so these are our reactants, turning into C and D, which are our products. What if we went ahead and added more of a reactant A to our reaction mixture that was in equilibrium? Well, if we add more A, then the system will want to minimize the stress of adding A. What does it mean, minimize the stress and shifting it in such direction? Well, if we added more A, minimization or relief of the stress would mean getting rid of that extra A that we added. Now the question then becomes, how can we get rid of that extra A? Well, according to Le Chatelier's principle, what must happen is reverse reaction, forward reaction must speed up. So if forward reaction occurs faster than the reverse reaction, that extra A that we added will be quickly converted into product, so we would be getting rid of extra A. So by adding A would cause reacting extra A away, and therefore the shift would occur to the right. So forward reaction would occur faster, getting rid of A by converting it into products. What if we were to, say, remove reactant B? So the second reactant here is B. Let's say I had a way to remove B from the reaction mixture, say by adding something that would convert B into a different substance. So I would basically be decreasing concentration of B. How can the system minimize the stress? Well, if I take B away, the system will want to make more B, right? You're taking it away, so the system wants to compensate for that by making more B. How can more B be produced? Well, to make more B, we need to speed up the reverse reaction. So C and D would react faster in the reverse reaction, producing extra B that we remove. So in total, the system would sort of compensate for removal of B by producing more of it. So next we're going to talk about what if we were to change the concentration of products. So for example, what if we were to remove reactant C? Once again, C is one of our products here. What if we took that away? reduce the concentration of C. How could system minimize the stress or compensate for lack of C or removal of C? Well, to make more C, forward reaction, where C is a product, would have to be sped up. Therefore, if we wanted to make more C, we would have to speed up forward reaction. So this means that equilibrium would shift to the right. Also, equilibrium can be shifted by changing temperature of the reaction mixture. And here it's important to distinguish between exothermic and endothermic reactions. So let's first consider a situation where forward reaction might be exothermic. You might recall from Chem 1 that exothermic reactions are those where heat or energy is produced. So in exothermic reaction, we basically consider heat as a product. So I rewrote the equation here, and I included heat here on the right-hand side, because if heat is produced, we can consider the product. So now what would happen if in such a reaction, where forward reaction was exothermic, what if we were to heat this reaction mixture? So we would be essentially adding more heat. Now, heat is a product, so this is sort of akin to adding more of a reactant, as we considered earlier. So what happens if we add more heat? If we add more heat, the system will want to compensate by getting rid of that extra heat that we added. How can system get rid of the extra heat that we added? Well, one way is it would speed up the reverse reaction, because heat would be then used up in the reverse reaction, and therefore equilibrium would shift. I hope you can answer with me. So again, if we add more heat, and heat here is a product, this would compel the reaction to use up that extra heat we added to minimize the stress, therefore shifting to the left and speeding up the reverse reaction. So here the shift would be to the left. Now, what if we were to cool our reaction mixture? Again, exothermic reaction, heat is a product, but now we're cooling our reaction mixture. If we're cooling the reaction mixture, we're removing heat. So we're removing the product. So if we're removing the product, the way the system will want to react is to make more heat. How can system make more heat that we're removing? By speeding up the forward reaction. And therefore, if we're cooling our reaction system with an exothermic reaction, we would then be shifting equilibrium to the right, speeding up the forward reaction and producing more heat. It's a different story if we're talking about an endothermic reaction. So what if forward reaction was actually endothermic? Just to review, endothermic reaction is the one where heat is absorbed. So once again, our hypothetical reaction, A and B producing C and D, but now because it's endothermic reaction, heat is being absorbed, so we treat heat as a reactant. Because in forward reaction, reactants are used up, and heat in this case would be also absorbed or used up. So now we treat heat as a reactant, not as a product like we did for exothermic reaction. So let's consider what happens if we heat our reaction system like this. Again, endothermic forward reaction, heat as a reactant. So if we add more heat, it means that system will want to get rid of that extra heat we're adding. How can system get rid of that extra heat that we're adding? It can speed up the forward reaction, therefore using up or reacting that extra heat away. So in endothermic reaction, heating the reaction mixture actually allows you to shift equilibrium to the right, making more products and using up the reactants, including the heat. What if we cool the reaction mixture in the situation where forward reaction is endothermic? Well, if we cool the reaction mixture, remember, we're removing heat. So this is similar to removing a reactant from the reaction mixture. So we're cooling, heat is taken away, the system will want to make more heat. How can system accomplish that? Well, one way to do it is to shift equilibrium to the left, speeding up the reverse reaction, which would allow then the heat to be used up. And so in this case, equilibrium will shift to the left. What will happen next is I'm going to actually record another video where I'm going to be doing the experiments described in your lab manual. What I'd like you to do when you watch that second video is to have your report sheet or data sheet ready and a pen or a pencil. So as you're watching me do this, you will be filling out your report sheet. And of course, if I go a little bit too fast because I want to keep these videos to reasonable length, you can always stop the video, make necessary observations and recordings, and then move on. I hope it will work well. Okay guys, till next time.